Live, live.
It's okay. Live, na? Okay. Good afternoon, dear participants. Good afternoon, Professor Subrata Chakravarti. He is working as a professor in the Department of Civil Engineering, Indian Institute of Engineering, Science and Technology, Sirpur, Kolkata, and which is the most prestigious institute and founded at 1856. And his research area include fiber reinforced composite vibration, structural health monitoring, earthquake engineering, dynamic analysis, uncertainty and reliability analysis. He has published 100 plus reputed international journals. Also, he has undertaken many consultancy works funded by state government, central government, and DST sponsored projects. He has received Suchit Kumar Ghosh Memorial Award in the year 2003, Young Faculty Research Award in the year 2005, INA Young Engineer Award, Indian Society of Earthquake Technology VH Joshi Award for significant contribution in structural dynamics in the year 2014. Also, he has received prestigious the Humboldt Research Fellowship in 2009. So, thanks, Professor Chakravarti sir, for to participate to joining with us as a resource persons. And I request Professor Chakravarti sir to say few words to our participants, actually, those who are in online. Just
What about the course or only to speak only about the lecture only, right?
No. Actually, our participants are generally faculty members, research scholars, engineers, practitioners, and students are there. Just to advise how to.
So how many participants? About more than 50?
Our sir 400, sir, 400.
400 participants.
Yes, sir. Yes, sir.
Hurry bus. What you did anyway. So first thing is that I thank you very much, Professor Pradhan, for inviting me. It's really when I heard from you that 400 people are listening to me, I'm really amazed. But at the same time, I missed your institute to visit. Of course, things will be normal very soon, and sometimes I have wished to visit your institute. I have heard about your institute number of times, but I've never visited it. So I will try to visit. I have visited your that Sambalpur, that Budla. Last
Yes, sir.
2019, I visited Budla. So I frequently visit Odisha. I went to Bhubaneswar and Rourkela. A number of times I visited those places. So it is nice to be connected with you. The participant, regarding my topic, I will tell you about this topic. Actually, as all you know that here there is a prestigious project is going on. Is about to complete in Calcutta. That is underground tunnel, east-west metro tunnel. So my topic will be a little bit interesting to you, but it is a very special kind of structure. And to be honest, 3 years back, I have no interest, I have no knowledge about these structures. But when this project came here, and I visited their project site number of times, so I get interested and I start to study. Otherwise, I mainly work on reliability analysis, vibration, etc. But this tunneling engineering is really a challenging field, and if you develop interest, you can do a lot of research on this subject. Particularly in India, there is very little work has been done, and there are a lot of scope, because after the success of this project in Calcutta, I believe there will be a number of underground such type of metro tunnel, metro structure on the other cities of India. Yeah, because you see this these things completely change the demography and the standing of a city. Just for example, you think about the London city. No, if you look to the London city in the underground, there is another London. You can't imagine so many tunnels, so many metro line, this side, that side. So you can practically visit all corner of London without coming to the surface by only by tunnel, underground tunnel. So once we get success in this Calcutta tunnel, I think things will change drastically in India. We will see underground tunnel very soon in our metro cities, other metro cities also. So that way I found this topic is interesting, and I Now, one of my PhD students is working on this subject. He has worked for 1.5 years. So we have recently developed interest, and we are trying to connect it with the reliability analysis, which is actually my field of research. But in today's lecture, I am unable to speak anything about reliability because 1 hour it may not be possible. So let me start, go to the content directly.
Yes, sir. Yes, sir. Yes, sir. Okay, sir.
I think this one. It is visible, no?
No, sir. Just share, sir.
I've shared, no? What it is? Anything? Share content. Now it's coming?
It's coming.
It's coming, huh?
Okay.
Okay.
Full
Just
screen.
just make it full screen, sir.
Yeah, it's full screen now.
Okay. Thank you, sir.
Okay.
Continue.
So,
Continue.
thank you all. Now, let me start the, because it is 1 hour. So, there are a lot of materials there. So, without wasting further time, let me come to the topic directly. So, my topic of discussion is an overview of underground tunnel analysis. So, what I try to put in this lecture is I will give you some overview or idea about analysis of tunnel as a structure from structural engineering point of view. As a structural engineer, how we look to the tunnel analysis problem, and also I will give you the basic things of safety assessment of tunnel structure, right? So before going to the discussion of the topic today, just let me show you one slide why I got interested in this tunnel analysis. You see, these are the photograph of tunnel works going on in Calcutta. It is called East-West Metro, and this tunnel is under River Ganges. So this is the place. Here it is behind the Howrah station. It is called Howrah Maidan. From here we enter to the tunnel, and it passes at the bottom of the entire Howrah station. Then it entered to the Ganges, and this place is below the river Ganges, 30 meters below the river surface. This is my colleague. These are my PhD students, and these are some of my former students who are working on the ECOM, who are involved on that project. You see, so this is about 6 meters diameter tunnel. There are two tunnels, one after another, and these are the lining supports, and this is the small train which bring us back. During upward journey under the Ganges, we went by walking. There is a walkway in this side, and we are so tired. We walk almost for 2 kilometers other side of the Ganges. Then when we are coming back, we come back with this train. This train actually now they are carrying the materials. Carrying the materials inside, and it is taking out the mud and all those which are after tunneling the material which are coming out. They are bringing it back. So when I visited in 2018, I was immersed, and I get interest on these subjects, and last 2 years I studied and I developed. In fact, one of my PhD students is also working. So this is my background of why I am in tunnel engineering today. Now, whenever we think about tunnel, we think that is a one tunnel. Only roads are there, and train and buses are running. But it is not like that. There are some other type of tunnel. If you look to this photograph, you see these are a typical tunnel under a mountain. This is the road tunnel, but there are tunnel like this. What is this tunnel? This is a tunnel, vertical tunnel to extract oil. This is a tunnel in the mining engineering position. So to mine the material. So this is a tunnel, then horizontal tunnel, vent are there. So these are various types of tunnels. So tunnels could be horizontal tunnel, it could be vertical as well for some specific purpose. So with this background, let me enter to the subject. So what is tunnel? Tunnel is an underground pressure passage excavated through surrounding soil rock mass for the purpose of highway, railway, or rapid transit. It could be pedestrian, it could be conveying fresh water, cooling water supply, wastewater collection or transport, hydropower generation or utility corridor. So these are the typical purpose for which we made the tunnel. And advantages are quite obvious. Avoid traffic congestion, which is a problem for big metro cities. Avoiding lengthy circuitous route in the hilly region. protection against weathering, acquisition of expensive land and property. So these two are most important: acquisition of expensive land and property, and avoiding traffic congestion. So these two makes it good alternative mode of transportation in mega cities. And safety to natural hazards like storm, avalanche, etc. Unfortunately, there is something happens in Joshimot area in last week, but that is some other reason. It is in the hydroelectric power plant. There is a tunnel, and still people are stuck within the tunnel. But their reason is something different. And there are some disadvantages, of course. There are two major disadvantages, I must say, two or three. One is the cost and time of construction is very high, and you need a lot of expertise. And most importantly, it damages the structure on the ground. When you are constructing a tunnel in the mega cities, it damages structure on the ground. You may remember it becomes a national news last year when there are a lot of damage on the structure on the ground in the North Calcutta area when the tunneling operation was undergoing after the Sialda and that before Sialda. From Sialda to Esplanade, when the work was going on in the central Calcutta, there are a lot of damage in the structures and we need to evacuate the people. So this is a major issue, damage of structure on the ground. And of course, depending on how you are constructing and what is the damage you are causing in and around the place of construction, so it destroy or it adversely affect the natural ecosystem of a particular area. You may not feel it when you are constructing in a mega city, but when you are constructing in a hilly region, otherwise which was a forest, green forest, there it affect the natural ecosystem. And I may say that this avalanche or this happenings may be some reason of this tunneling operation. There may be some remote connection with those glaciers break or all those things. Because when you are making a big tunnel, you are completely destroying the rock mass in and around. We will show this in the later picture. So that completely destroy the natural ecosystem, stress balance in the region that get lost, and that may lead to landslide or avalanche slide, etc. So that is another important issue. So these are the typical shape of tunnel. It could be like this. And not only the single shaped tunnel, there are two or three tunnel, one after another. Particularly for east-west metro and Ganges, we have two tunnel, one after another. Each are equal size, identical, but one after another. Right. So these are the typical site. Most common is the circular section, and the earlier days it was rectangular section. Still, rectangular sections are used for some service purposes, and this is horseshoe section is a quite good economic section. Egg-shaped sections are also available. Depending on the purpose of use, these are the typical sections available. Right. And now if you classification, the tunnels are mainly classified in two major hubs. One is the traffic tunnel and another is the conveyance tunnel. Right. Traffic tunnel are for highway, railway, pedestrian, navigational tunnel and subway. And for conveyance tunnel, it could be water supply tunnel, fuel tunnel, hydroelectric power station, transportation tunnel in industrial plants. There are a number of tunnel in a typical big industrial house. Tunnel for intake and conduit of public use. So these are the typical type of tunnels we see in and around. Right. Now, a small one slide regarding the history. So the tunnel was first constructed by the Egyptian and Babylonians, and I can imagine it was constructed sometimes in 2160 before BC. So, and it was almost 1 kilometer length and cross section is 3.6 meters by 4.5 meters. So a rectangular tunnel was constructed along that, right? And the first, longest and the largest road tunnel we see between the Naples and Fuzuli, and which was executed in 36 BC. So tunnel has a long history. And modernization with the use of gunpowder in tunneling for blasting the rock mass. It makes 160 meter length of tunnel in France in 1680. So fast use of gunpowder in tunneling. So it is parallelly with the fast use of gun for fighting purpose. Yeah, around that time, right? Then nitroglycerin and compressed air was introduced in 1850. Tunnel ventilation was introduced in 1927. So these are the hallmarks in the history of tunnel construction. And the major was another hallmark is use of shortcut in tunnel lining. That means to support the tunnel around the tunnel. Shortcut was used in tunneling. That similar concrete prevar block I show you in the picture. Similar kind of things or shortcutting was used in 1920. And the revolution in the tunnel engineering was introduction of tunnel boring machine. That means the entire process was practically automated. There are a lot of YouTube video available. I will show you one such link also, so you can see those. It entirely makes the things automated, and it makes a revolution in the field of tunneling. The use of TBM, tunnel boring machine. Right, this is the small history. And regarding the milestone in tunnel construction. So the world's longest tunnel is 170-kilometer aqueduct between Delaware River to New York City to supply. It supplies practically 50% water supply of the New York City. And the world's longest passenger carrying tunnel was 57 kilometers in Switzerland. It is called Gotthard Base Tunnel. This tunnel, I visited by train on this tunnel, fortunately, but I was not aware at that time that I'm going through the longest tunnel. And this is our own India. India's longest railway tunnel was Pir Panjal Railway Tunnel, which was inaugurated by our Prime Minister in 2013. It is in Jammu Kashmir, 11.2 kilometer, and it is in a strategic location. It is a strategic location with respect to our neighbor countries. And this is the India's longest road tunnel. It is called Samaprasad Mukherjee Road Tunnel. It was inaugurated in 2017. It was on NH44 Chenani. It is commonly known as Chenani Tunnel. Right. So this is all about little bit of history. Now I will enter to the subject. Oh no, there are another two slides regarding tunnel construction. So tunnel construction, the most popular method 20 or 30 years back was cut and cover method. Still we use this method for small tunnel in many places. So for shallow tunnel, a trench is initially dug as per the requirement and overhead roofing system is provided. That means you open, you make a dig and remove the soil or the rock, make a trench, then according to your requirement, you construct the structure. And if you look to the step of construction, you can realize. So there are two approaches. One is bottom up and one is top down approach. So what is done? So you see, these are the sheet pile support wall. Then you remove the material. Then you make it complete space, trench. Now in this trench, you make your structure. This is the tunnel. This is one tunnel. Now in this tunnel, you can run your train or car or bus. Actually, I think I believe some of you may have traveled in metro tunnel in Calcutta, existing metro. Those are cut and cover type of method. At that time, I was undergraduate student. I was in third year, final year, and that time we have seen that cut and cover process of tunneling. Right. So this is a bottom up approach, and this is a top down approach. In bottom up approach, everything is removed. Then from the bottom, construction is going. And in the top down approach, you remove little bit, then make a construction, make a house and arrangement to remove the material, then keep on removing the material and gradually keep on constructing towards the downward side and make the tunnel. Right. So this is called cut and cover method. So cut, make your structure, then cover. Okay. And then this is possibly the oldest method, clay kicking method. This is an old method of tunnel construction generally applied in strong clay soil for small works like base line installation. So he is giving a pressure and make a hole and pass the small pipes. And this is called shaft method. You make a vertical shaft and then go up to the height, then make the tunneling at this process. And later on, this shaft is used as the exit point for the tunnel. And there are some popular method for small work. This type of tunneling is used. Pipe jacketing method. It is a shallow tunnel with a maximum size of 3 meter or 3.2 meter. Generally under. Again, I am in class. Sorry. Pastor pore korbi? Pastor pore korbi. হ্যাঁ 5টা 10টাতে করে 5টা 10টাতে করে ঠিক আছে আমার ক্লাসটা 5টা অবধি আমি ক্লাসে জয়েন করব So this is generally under existing structure. So what is made, a specially made pipe is pushed by a hydraulic jacketing system into the ground at required location. Actually nowadays if you see the electric supply company, they are removing all the overhead line by underground line. Now the work is going on in front of my college in Howrah. That CSC Calcutta Electric Supply Corporation, they are doing it. So it is a very interesting thing. There is one car and there is one hydraulic jacking system is available on motor is running, and they are pushing the pipe, and within the pipe they are pushing all the cables. So this is a handy method. So they are taking at a stage, say 50 meter or 60 meter stage, completing it, then another joint, then again making another one. Now what is going on in front of my house? It's an interesting one, pipe jacketing method. And this box jacketing method is a little bit bigger than the pipe jacketing method. Here you are pushing a pipe, here you are pushing a bigger one box made of concrete or pre-stressed concrete garden, a pre-stressed concrete, and this box is pushed one after another, and you make a conduit or a trench and accessible place under the box. This is another way of making, and this is another interesting method, is immersed tube method. So what is done? A series of precast tubes are immersed underwater. So you see this type of precast tubes are not, this is hollow. No, this is the end section. That's why you cannot see here, so that water cannot enter. Now it was taken by a ship to the desired location. Then it was placed under the water. Then it was connected properly, and another one is connected from this side. Now once connected with the another one tightly, then this temporary wall is removed, and you get the entire space. So one after another like this, and at the end you will get the entire tunnel. Earlier, before TBM, this was a popular method for tunnel construction, and it is pretty construction, because everything major construction you are doing on the ground, you are simply taking it through vessel to the desired location and placing one after another and connecting, then removing this temporary. This is called immersive method. And the last one is the tunnel boring method. You see, this is the tunnel boring machine. This is the front end. So it cuts through this line, and material will fall here. Then it goes there. Then it goes here. Then it goes to the cargo, goes to a trolley, and the trolley runs over a rail. It takes outside. The way they are doing in East-West Metro under Ganges. So as I told you, TBM makes the revolution in the tunnel. Now everything is automated. But the problem is that the major problem of using this method is the transport and handling of the heavy TBM. Not only that, the major issue is its cost. This machine is huge costly. Say per day, actually in Calcutta they are using the machine. They got it from Australia, and you know per day you have to pay 7 lakhs for this machine per day. 7 lakh. And when you will operate this machine, you have to get an engineer from Australia, and his salary per day is another, say, about 1 lakh per day, right? So this is the problem. That means if you cannot work with the TBM for 10 days, then you to 20 days, then you have to simply pay 1 crore rupees without doing nothing. So this is the difficulty. That's why the TBM cannot be used unless it's a major project. Of course, there are small form of TBMs are available. Particularly, we have used one such TBM for working when we are taking water from Ganges to Rajarat, New Town City. Then there was a water pipeline, 1.3 diameter water pipeline, and we need to make underground tunneling in some places. That means when it was crossing the roads, no, we have not made cut and cover. When it was crossing through the roads, we make this type of tunneling, and directly we put the pipe below the roads. So there also we have used small TBM. But for a bigger tunnel, say it is 3 meter or 5 meter diameter, we don't have any such tunnel in India, and we have to get it from abroad. And cost is around. So what cost I was saying is per day 7 lakh. It was the cost in 2018. I heard about that. Now it may be more than that. So that is another difficulty with the tunnel boring machine. Otherwise, everything is automated. And if you see nowadays, there are very little accident in tunneling operation. But even in Calcutta Metro, when it was in cut and cover in our time, there are a lot of accidents, particularly to deal with the pressure, air pressure underneath, and the sound problem. There are a lot of health hazards there. Nowadays, it is perfect. You see, below Ganges, they did it smoothly. There is not a single accident. Nothing happened. Almost 1 meter, 1 kilometer tunneling under the water. Nothing happened. Now let us come to the structural analysis of tunnel. So the construction of tunnel causes disturbance in the equilibrium of existing stresses. And normally, why disturbance occurs in the existing stresses in a rock mass or a soil mass? Due to surcharge pressure, due to tectonic pressure, due to earth crust movement, loosening pressure due to tunnel driving, and redistribution of pressure due to disturbance in the stress. Let us look to the fundamental. Fundamental is like this. You see, when there is nothing, if you look one position here, what is the stress? Each and every point, if you look to the stress, it is a uniform stress P, right? P everywhere, everywhere. Now, if you make a hole here, tunneling, you are making a hole here. If you make a hole here, now this stress distribution gets changed. How it change? So this is called secondary distribution. So in and around the hole, you will find stress will increase and stress will decrease gradually. After a certain distance, again it will get to the virgin stress, right? And I've shown you two diagrams. The reason is that if your this soil mass is not brittle matter, so the soil mass is nature is in yielding type or brittle type. Depending on that, the distribution could be like this. So if the nature of the soil is brittle, that means if it is a rocky mass, then in and around there will be high stress and it will diminish within a shorter distance. But in a soil mass like clay soil or something like that, for shallow tunnel particularly, then you will find that in and around tunnel stress may be low less, but it will take a large distance to distribute to a zero level. That means it will affect a larger portion in and around the tunnel, but it will affect a smaller portion in and around the tunnel. So this is the structural engineering. Stress was like this, stress is becoming like this. So we have to forecast this stress distribution. That is the task of structural engineering. Right. So if you look to the problem in structurally, basically it is really realistic analysis of tunnels and underground excavation required a 3D model. Right. So this is your ground mass. I have taken a certain diameter. So this is the tunnel is going on. This is the say this is your tunnel lining, shotcrete or concrete lining below the tunnel. And after that, up to certain distance, up to which it has effect of the stress. So you consider the entire as a cylinder. So it's a three-dimensional problem, finite element problem. And normally we make a two-dimensional idealization for ease of analysis. Now there are two approach of analysis. One is called equivalent continuum method. It is most popularly till today we use this method. A lot of literature is available and a lot of design techniques are available based on the equivalent continuum. What is that? In and around the tunnel up to certain distance beyond which the effect of tunneling operation is nullified, that soil mass or that rock mass is considered homogeneous, continuous, on continuum, and we make the stress analysis accordingly, right? This is called equivalent continuum model. This is the popular and famous one. And nowadays, most advanced methods are developed. It is called discontinuum. What is that? In and around, actually, there is no continuum and homogeneous soil. There are rock mass, one type, little bit distant, there is another fracture rock. So it model rock by rock. So what is the idea? I can give you a small idea about these two types. One is say you are analyzing a masonry wall. Right. In equivalent continuum model, entire wall you consider as equivalent elastic property, and we perform the stress analysis by finite element modeling. So this is called elastic continuum. Single one e value we give and make the finite element model equivalent e value. And in discontinuum model, you model the entire domain brick by brick. Along with your in between two brick there are mortar. So one brick, then mortar, then one brick, then next brick by brick model. That is called discontinuum model. So nowadays these models are becoming popular because these are much more accurate. You can get better idea about the stress distribution along the tunnel and across the tunnel. But it is, as you understand, it is really difficult and you need a lot of input data. So if you have enough geophysical data around the region, then you can go for that. Actually, we have just started this type of work, but it is really a tough job. And still, almost all the tunnel analysis you will find equivalent continuum model. Through a diagram, I will just give you the idea about this. Oh, before that, let me just show this slide. What are the various numerical methods used for stress analysis of tunnel? One is continuum model. I have already told you what is continuum model. Then discontinuum model, and this is the subgrade reaction model. Earlier days, beams on elastic foundation type of method. That means the entire tunnel is considered as a beam, and the rock mass is giving a elastic reaction. So you consider elastic spring around the beam. This is a much more simplified method, but in the early days we use this method. continuum model is nowadays we use, and you can apply finite element method, boundary element method, or finite difference method. A finite element typically we use Abacus or ANSYS software, and finite difference flag software is used. And discontinuum model, it is emerging. So here I will get the continuum and discontinuum. So this is the actual, I told you, the three-dimensional problem, and this is the three-dimensional, it is the continuum model. What is this? So along the tunnel, you see, entire mass is called the continuum, and for each mass we discretize it to finite element, and for this element, this element, this element, this element, we give the equivalent stiffness property or the modulus of elasticity or the shear value, etc. those properties. And here you see, this is the tunnel, and around the tunnel each and every is modeled block by block. This is one block, one property, another block, one property, one property. So this is called discontinuum modeling. Actually it is called synthetic rock mass modeling. There are advanced procedures. If you know a lot of geophysical data around the tunnel in this region, then it is possible to develop artificially the rock profile along the tunnel and across the tunnel direction, and you can perform the analysis accordingly. It is much more sophisticated, much more advanced, more realistic, of course more complicated, and practically readily available softwares are not available for this. Okay. So in nature, all problems are three-dimensional, but we can bring down it to a two-dimensional plane strain or axisymmetric approach under certain assumptions. What are the? I will come to those assumptions later. So the plane strain approach can be used for shallow tunnels, and axisymmetric approach can be applied for deep tunnels. And in combination of plane strain and axisymmetric analysis, you can simulate that three-dimensional analysis. One result I will show where we have done the plane strain analysis in combination with the axisymmetric analysis to get the entire deformation configuration of the tunnel. So various material models. So when we do the finite element analysis in continue, whatever I am talking now is continuum model, right? So material would be linear elastic models or elastoplastic, right? And for elastoplastic models, there are number of elastoplastic behavior models are available. One is most popular one is the Moore-Coulomb criteria, then generalized Hoek-Brown criteria, and Drucker-Prager strength model. This model is hello. Anything? Okay. Yes, it is echoing or someone is saying something. Anyway, Drucker-Prager strength models and viscoplastic models, right? Also, different reinforcement elements can be simulated, including rock bolts, rock dowels, and rock anchors. Shortcrete, that means tunnel supports, are also possible to model using beam element or plate elements. Now, elastic analysis. So, you see, this is the problem. When you are making a two-dimensional analysis, then you are taking one cross section only, and if you consider one cross section, this is the tunnel opening, and this is the length, this is the how much length beyond which there is no effect of increased stress due to the tunnel opening. Hello. So this is the problem. Structurally, problem is, you see, it is a plane strain in cylindrical coordinate system or theta coordinate system. So it is subjected to a pressure P0 to gamma and what is this is the virgin pressure. That means at this point pressure is maximum and it is coming down, 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 and at that point, so up to how much distance you have to perform the analysis, beyond which pressure is a virgin pressure. So this is called hydrostatic pressure. And when this condition will be satisfied, the plane strain conditions are like this. Rock mass is homogeneous and isotropic. Tunnel subjected to far field hydrostatic stress. That means this one, far field hydrostatic stress. No variation of stress with the depth. You see here and here uniform, but in real it will be not. It will be little bit triangular. But we assume like this. Then the tunnel is deep. The tunnel is deep, and strain in longitudinal direction is negligible. That means this direction is so long that the increase or decrease of length along the axial direction can be neglected with respect to the radial deformation of the tunnel, and cross section is circular. So these are the conditions. Under such conditions, you can perform analytical approach of analysis of tunnel, and this analysis is a very simple one. I think those who have the master degree in structural engineering, you know how to perform the plane strain analysis under earth theta coordinate system. So we consider a small rock element or element, stress acting here, CR at a distance dr, this like this. So this is a small element, no, of dr, length of dr and angular d theta. Then the equilibrium equation is this one, static equilibrium. This is the stress-strain relationship in 2 dimensions. It is standard for plane strain element. And this is the strain displacement relationship. And now for solving this equation, you have to solve this equation. To solve this equation, we will use the boundary conditions. So what are the boundary conditions for this problem? The boundary condition at r equal to infinity, that means at this surface, when r is very large, sigma r and sigma theta is nothing but T0, right? And there will be no strain because effect is nullified. So if you apply this boundary condition, you can easily get the solution. Solutions are like this. So these are the solution of an elastic solution of a tunnel analysis problem when you are considering it as a plane strain problem. When it is possible to consider it as a plane strain under those assumptions. And these are the solution. That means you can find stress. What is the stress here? Sigma r and sigma theta. Put it in this equation. What is the strain here? What is the displacement at this point? Put in this equation. But so long in and around the entire material is elastic. But it may not be elastic when your tunnel is so large that stress developed here is so high that this material has yielded. If material has yielded, this solution will not valid. You have to go for the elastoplastic analysis, right? So for elastoplastic analysis, what is it? I can remove this part.
Sir, your voice is not audible. Sir, you have mute your voice, I think. Just check it. Sir, your voice is not audible. Mute your voice. Just check it. Sir, you just unmute your voice. Actually,
Now?
yes, it's now fine. Just continue.
Okay. How it happens? Okay.
Continue.
Now I am audible, no?
Yes, sir.
Okay. Okay. So now, if the stress, so if there is a small hole, there may not be high stress, but if you make it, there are a lot of loss of confinement. Okay, I am audible now. Hello.
Yes, sir. Yes, sir.
Okay. So if there is a lot of stress, the stress value is magnitude is very high around the tunnel lining, then the tunnel material will lose its elastic property, it will yield, and this yielding will gradually expand it toward the outward side, and that part needs your elastoplastic analysis. So now here we have introduced a pressure on RP. What is RP? Up to which portion the yielding has occurred, and this is the critical pressure. That means the value of the pressure at which it starts to yield, and it will depend mainly on what is the external pressure you are applying, P0, and the soil property or rock property around the tunnel, right? So P critical you can calculate from the material property. So if the stress developed is more than P critical, then it will yield, and the yielding will start from the face of the tunnel and it will spread outward. And if the pressure developed is less than the critical pressure, there is no question of yielding, so it is a completely elastic analysis, right? Otherwise it will be elastoplastic analysis. So when P critical, the material property is such that, and the stress developed at the face of the tunnel is such that it is greater than the P critical, then there is no question of yielding, and it will be standard plastic analysis. That means the solution whatever we have derived earlier, right? This is the solution. This relation already we have derived earlier. But the problem is when P critical becomes more than the pressure, then it will start to yield. And say the formation of plastic zone is RP is the radius, RT is the radius of the tunnel, and there is a outward spreading of the plasticity, and up to what distance? Say up to the distance of RP. And now you need the failure criteria, as yielding means it's a failure. So when you will analyze for a failure, that means inelastic stress distribution, then you have to define some failure criteria. So we use usually Moore Coulomb, Hook Brown, and other also. Now I will briefly discuss these two criteria, Moore Coulomb and Hook Brown failure criteria. So this is the scenario. That means you see this is the RT tunnel diameter, and the diameter is such that, and material is such that it has yielded, and it has yielded up to this position. And after that, the stress level is such that soil can sustain this. So this is the, so this portion will be governed by elastic analysis. This portion will be governed by plastic analysis or elastoplastic analysis, and this is called elastoplastic boundary. Okay. So this is the definition of the problem. Now this is the typical Moore Coulomb criteria. This is the subject of soil mechanics. I don't know much about it. So this is the typical Moore Coulomb criteria. Shear stress equal to cohesion plus normal stress into the phi angle, that means the friction angle, and we know that tau equal to sigma r minus sigma theta by 2, and c equal to sigma theta plus sigma r by 2. So if you substitute it here, and equation will be simplified to this, where sigma r and sigma theta is the circumferential and radial stress developed at any point, and these are the relationship we have already solved. And if you apply the boundary condition, what is the boundary condition? Note at r equal to rp, where it is now, it is the elastoplastic boundary. At that point, why it has been? It has just yielding started. So at that point, pi equal to p critical, and if you substitute this pi equal to p critical and sigma and sigma theta in this equation, then that will be simplified to the this one. What is this? You see, this is the radius of the plastic zone. How much? The radius of the tunnel multiplied by these things. What are these things? Kp is the coefficient of pressure. We call it active arc pressure coefficient, passive arc pressure coefficient, 1 plus sin pi by 1 minus sin pi, and this is the uniaxial compressive strength of the rock mass. So these two are the purely the property of the medium, and with respect to the property of the medium and what is the hydrostatic pressure acting on the tunnel, based on that you can decide what will be the radius of the plastic zone. That means how much zone has yielded, right? And this is the solution. Earlier we have shown the plastic radius, and this is the solution. Displacement anywhere you can get, and the critical pressure. These are the expression. So those solutions are based on Moore Coulomb criteria, and there is another famous one. In fact, this one first developed in the field of tunnel literature, but it is a little bit complicated. Anyway, so Oak-Brand criteria is basically an empirical criteria. In Moore Coulomb criteria, we have assumed a linear failure criteria, but here we follow a nonlinear parabolic form, and it is, as I told you, it is empirical. All things I cannot explain. So this is the failure criteria. Oak-Brand proposed sigma 1 equal to sigma theta plus sigma ci into this, where there are a lot of parameters. Where M is defined like this, where it has Mi and GSI, geological strength index. A is defined like this, S is defined like this. These are empirical relationships based on the observation and actual stress analysis. They derive it. Sigma 1 and sigma theta are the major and minor principal stress at failure. These are typically sigma r and sigma theta. Sigma ci is the unconfined compressive strength of rock. Again, material property. M, S, and A are the material constant of the rock, right? And GSI is the strength index, depending on the nature of the medium. D is the disturbance factor. If you are making a blasting, then you have to take 1, otherwise it is 0. Okay. So if you substitute this value and simplification, you can write down the Hook-Brown criteria in this equation. P critical equal to P0 plus M into sigma CL, and M is defined by like this. M comes from this. So major thing is GSI, how we get this thing. For defining the geological strength index, there are recommended value 80, 70, 60, 50, 40 like this, like 10, depending on the type of. If it is a complete blocky material, blocky rock, then you can take anything between 80 to 70. If it is reasonably or very blocky, then anything between 60 to 50. If it is blocky but disturbed for some reason, then you have to take between 40 to 30. So that way, and if it is disintegrated, poorly interlocked, heavily broken rock mass, then you have to take between 20 to 30. So this is the guideline to take values regarding geological strength index. And this is the typical stress strain behavior of the rock mass is considered. If it is a yielding kind of nature, then you use a peak strength. There are lot of deformation before breaking. But if it is a brittle kind of thing, then we take like this, idealized residual. So, but you see, there are a lot of residual strength. So for residual strength, these are the formulas. What are the GSI value for the residual strength? This is the formula. These are the formulas, right? So you can calculate it from the original GSI value of the rock mass and put in the exponential equation. You will get the parameter SR, from here, from this table, right? Once you get these values, you can calculate the final stress and strain failure criteria. And plastic zone radius finally comes out to be RP equal to RT into this one. Where M1, MR, sigma C all are obtained empirically, but it depends on the property of the rock mass. So this is a brief summary about the Hopdown principle. And if you graphically see what is the difference, so this is the Moore Coulomb criteria and this is the Hopdown criteria. So if the sigma 1 and sigma 2 is anywhere, sigma 3 and sigma is anywhere within this region, then it will not fail, the soil must not fail. But if the stress is anywhere outside this region, then it is a failure case. Now, where is the difference? You see the difference. You see, this is a linear failure surface. No, it is a linear failure surface. But here you see, this is a parabolic failure surface. So, Hopdown is more realistic in terms of rock property. Right. But when to, so if your tunnel is around the soil mass, rocky, not rocky soil, but clay soil or sandy soil, etc., then we prefer Moore Coulomb failure criteria. But if your tunneling operation is within a rock mass, then we prefer Hopdown failure criteria. Now the method of analysis, design method. It is called convergence confined method. So convergence confined method is the most popular method as it is. By the way, it is up to 5. If I take 5-10 minutes more, it will be okay. Or I have to close by that. Professor Sujit. Hello. Let me complete. So what is the meaning of convergence? The relative displacement of a pair of diametrically opposite points at a section in the tunnel is called the convergence. That means the tunnel try to come close to each other. That is called the convergence. And the convergence depends on several factors: the distance between the ongoing tunneling phase and the measurement location, time
Hello,
taken
sir?
to the. Yes.
Any problem, sir? Just
No, I was talking. If I take 5-10 minutes more, will it be
no,
okay?
no problem, sir. You can continue.
Okay.
Okay.
Maybe 5 minutes or 10 minutes more. Okay.
No problem, sir.
Okay. So the analysis is influenced by many factors. What is the depth of the tunnel, variation in the condition of the rock mass, that means the medium property and shape of the tunnel. And necessary assumption, if you look those assumptions are the same assumption we made for plane stress and axisymmetric case. So it has to be deep tunnel, circular tunnel, hydrostatic pressure, homogeneous, and 2D plane strain. That means all assumptions are 2D condition. That means the CCM method is under the assumption of 2D plane strain condition. Now the CCM method rely on 3 basic plots. What are those plots? These are called ground reaction curve, longitudinal displacement curve, and support characteristic curve. I will try to explain what these things mean. So this is called longitudinal displacement profile. What is this? You see, this is the curve. This is the face of the tunnel. That means tunneling has been done from this side. It is going up to this portion. Tunneling has been done, and this is called face of the tunnel. Now you see what is the displacement. So when you are cutting, the tunnel has come confined, convergent towards this side. This much is the displacement. If you look to the away from the tunnel, already this portion is open. So what is the displacement here? At a distance of this is the displacement. At a displacement here, this is the maximum displacement. After certain distance away from the face of the tunnel, then it reach the maximum value and there is no further increase. So this curve is called the longitudinal displacement profile of the tunnel. That means you think you are cutting a tunnel. What is the convergence of the tunnel towards each other along the axis of the tunnel? Right. So this curve is called LDP, longitudinal displacement profile. And what is this? This is called ground reaction curve. That means the corresponding tunnel wall pressure. So when you are making the tunnel is coming to each other. What is the pressure acting on the tunnel? At that point, what is the pressure? So pressure versus displacement, what is called ground reaction curve. So you can remember now, when there is virgin soil, pressure is P0 equal to gamma into H. When you are making a tunnel, maximum pressure at the face of the tunnel, and it is gradually decreasing. Now, this pressure versus displacement is called, at a particular cross section, pressure versus displacement, what is called the ground reaction curve. Okay. And next is your support characteristic curve. What is that? It gives the final displacement of the tunnel wall after installation of support. That means when you have installed the support, what is the support of a tunnel? You are opening the tunnel, then making a shotcrete or making a concrete lining or making a paver pre-stressing block or giving a steel shuttering kind of things. Order. That means you are providing something to support the tunnel so that it does not collapse. Right. So this is the support characteristic curve. It gives you the final displacement of the tunnel, that is displacement of the tunnel along with the displacement of the support which you are providing to hold the tunnel, and the final internal pressure developed. So this curve, this small curve from here to here, that means what you see, your initial is already tunnel has converged before installation of tunnel. Now after that you are now installing the support, still it is displacing. That point it start to displace, and this curve, this small curve, it is called the support characteristic curve. How to get those curves, I'll discuss. So this is the ground reaction curve. How you will get the ground reaction curve? Very simple. If you apply Mohr Coulomb formula, then we have seen this is our formula of displacement. We have seen this solution in our elastoplastic analysis. So P0 is a known value, pre-critical is a material property, RP we know from the Mohr Coulomb criteria. So you keep, you will get RP if you vary the pressure P critical, P0, P critical and P0, and make a plot PI versus URP. All other are known. So variable is PI. So for different PI, you can immediately calculate the displacement and you will get the plot. This is called ground reaction curve. Okay. These are the parameter unit in this equation. And longitudinal displacement profile, actually it is basically to get this curve, you really need a three-dimensional solution. But we are not doing the three-dimensional solution. So some empirical relationship are available. There are two equations actually available. One is this one for this region, for that means to get the plot of this up to this portion. What is this portion? This portion tunnel was not made. And this is the face of the tunnel. This side already we have the tunnel. Here the rock mass. So at that portion still there will be some displacement. That displacement is obtained from this equation, and another equation. It is an empirical equation, and this gives the displacement profile of this portion of the curve. And it has been empirically derived based on number of nonlinear limit analysis result. Then they have calibrated this equation for your ready use. This is called longitudinal displacement profile. Right. And finally, the support reaction curve. As I told you, it starts from the U initial. What is this initial displacement? You will get it from the longitudinal curve. At what point you are going to put the support? At that point, already you know the displacement from this curve. From this curve, say at this point we are going to put the support. So this is your initial displacement, this much. No? So it is already known. So from this point, it is a linear elastic up to which portion? Till the support fails, yielding. And if support yields, then it is completely perfect. So elastoplastic. And how you will get this point? It is connected with the property of the support, whether it is made of concrete or it is made of steel. You know what is yield strength, so you can get this point. So this is the support characteristic curve. Right now, how you will get this? So support characteristic curve depends on the elastic stiffness of the support, initial displacement before installment that I told, at what location you are studying the design, maximum support capacity that gives you the Pmax value, and allowable maximum displacement to the support, that is in the Umax value, maximum how much displacement is. So this is your elastoplastic support characteristic curve. And now you see there is a cutting point in this curve. This point is important. This point is called the design pressure. That means your support should design for this much pressure. And so you need the K's value, and K's values and all those quantity tables are available. If it is a steel set, if it is a shortcut lining, if it is a rock bolt lining, so values are available. Now you see, just I will explain you in the both the curves simultaneously how you will get the design point of the. You see, say you are interested to check the safety of the tunnel at this point, right? This is the face of the tunnel. At this point, we are going to provide the support. So, what will be the capacity of the support? At least we should provide for safe design. So, at this point, you go there. What is this? This value is the initial displacement. So, go horizontally, come here, it cuts here. So, this is the initial displacement. So, from here, this is 1 point. Oh, sorry, this is 1 point, and you know this PS maximum. Depending on the type of the support, if it is shortcut or steel, based on that, you know this point. Make a horizontal line, you will get this line and get this line. So this point to this point. And how to get this slope? Again, stiffness of the support, right? So you get this point. Now, when you add this line with this line, it cut at this point. So from this point, you go horizontally. This is called the design pressure, which your support should at least carry. Then your tunnel will be safe. So this way we design the support pressure. And once you get the design support pressure, you can easily now proportionate what is the thickness you should provide along with the safety factor. Right? So that is the basic idea of convergence confined method. You get the LDP curve, you get the GRC curve, you superpose the SCC on that, get the cut point, get the, so ultimately getting this value is the purpose. So this is, I have taken a finite element analysis of a tunnel, a circular tunnel with concrete lining. These are the properties. Just I will go through the modeling. So we have done it in abacus, 4-noded bilinear plane strain element. You see, these are the element, and the element size decreased towards the tunnel opening, and it is bigger towards the outside the tunnel. And concrete lining is also model. It is a model as a 2-loaded linear beam element. So this red one is the concrete lining. So we have modeled it as a beam element, and we perform the finite element analysis. Now, one important point I should point out here: surface to surface interaction. That means, you see, this is a soil or rock mass, and this is a concrete mass. These are two different kind of materials. So you have to take care about the interface modeling. In abacus, there is a facility, surface to surface interaction. It is possible. Only you have to do, you have to define one material as a master material and another as a slave material. Then surface to surface interaction is possible. It is very easy. And in this model, we have identified the rock mass as a master material and this concrete lining as a slave material. And this is the displacement contour of the tunnel, and this is the major principal stress contour of the tunnel. It's giving me one reminder, already 4. Okay, I will take another 10 minutes. So this is the stress distribution, and this is, again, we have done the longitudinal displacement analysis. This we have done as a axisymmetric element, right? 3-noded axisymmetric triangular element, similar kind of. I've taken certain length of 50 meter uncut and 50 meter cut sections for stress analysis. And we have performed the finite element analysis again in abacus. Then this is the displacement profile we have got. These are the results of displacement profile of the tunnel. That means LDP. Now I will go to the safety assessment of tunnel. You see, this is very difficult to cover in one class. Actually, safety assessment of tunnel means reliability analysis. I really cannot cover reliability analysis. Just one slide I will show. Then I will go what are the major things we should consider during reliability analysis of tunnel. So what is reliability analysis? Reliability analysis is basically you have to satisfy a safety criteria. Z. Z, if it is less than 0, that means your limit state equation. Then it is safe, otherwise it is fail. So probability of failure is, what is the probability that Z will be less than equal to 0? It is a multidimensional integration which is not possible to get solution for real engineering problem. You have to make approximate analysis, either Monte Carlo simulation or a first order bit analysis. So I am skipping this part because reliability analysis itself, at least it needs 2 to 3 hours lecture. So forget about this. This you will learn. It is not connected with the tunneling. It is connected with the mathematics of structural engineering. Actually, I teach this subject in postgraduate level. It is a 1 semester course. So forget about this. Just you see the connection of reliability analysis of tunnel is here. How you are defining the limit state equation. That safety definition of the tunnel. That part is important. Otherwise, remaining part, once you define this GX equation, remaining part is like any mathematical reliability analysis. So you can forget about it. So what happens due to excavation of tunnel, the stress around the void are redistributed and the rock mass is disturbed, right? So the failure mechanism, one is called structurally controlled instability and another is called stress control instability mechanism. So we will consider structurally controlled, that means formed by intersecting discontinuities and the jointed rock mass is considered as equivalent continuum. So this continuum approach we are using here. So let us see what is the failure criteria. First one is the performance function is like this for reliability analysis of tunnel. What is this? Maximum allowable inward displacement and resulting inward displacement. So tunnel has a tendency to converge towards each other. Na? If you look at diametrically opposite 2 points, they try to come each other. So there must be some limit. If it is beyond that level of convergence, then tunnel will collapse. So this is one criteria. And more the convergence, more the radius of the tunnel. So normally we normalize with respect to the radius of the tunnel. So finally, G1x is defined like this. Epsilon is the allowable value and URP is the maximum displacement of the tunnel divided by the radius of the tunnel. And epsilon is the allowable value. Typically, it is 0.1% or something like that. Right. Now, another criteria is the rock mass will collapse towards the tunnel opening only after reaching a certain plastic. You have shown no? There is a আমি না ক্লাসটা এখনো চলছে 10 মিনিট চলবে আমি তারপরে কথা বলি আমাকে দেবব্রত আমাকে ফোন করেছিল আমি 10 মিনিট পরে কথা বলবো হ্যাঁ So you see, if the plasticity goes outward way, if it is a small distance, it will not hamper or it will. But if the plasticity flow is a large diameter, that means if the RP is very large compared to the diameter of the tunnel, then all the tunnel all on a sudden it will collapse. That means there is a maximum allowable level of plastic radius of the tunnel RP. Okay, so this is called lambda RP max by RT. So there isn't some allowable value of lambda, and this is the second limit state equation. We define it. G2x is lambda minus RP by RT. What is the actual radius of the plastic zone and the radius of the tunnel? This ratio. And what is the allowable value? Typically, we take value between 2 to 3. If it is within 2 to 3 RP by RT, then you can think that your tunnel will not collapse, right? So this is another limit state equation. But here I have written 3 to 5. But normally people keep it in within 2 to 3. Then another criteria is that the support should not yield. So what is the maximum pressure support can take? It depends on the thickness of your concrete lining, grade of concrete, whether you are making M40 concrete or M50 concrete, etc. Normally high level of concrete grade is used, or pre-stressing concrete, whatever you are using. So what is PS max and what is PSD? PSD is the common cutting point. That PSD should be sufficiently lower than the PS max. So that is another failure criteria. So we call it G3X PS max minus PSD. And sometimes along with the lining, we give rock bolt within the tunnel to strengthen the rock mass or the soil mass around the tunnel opening. So there is another failure criteria. Rock bolt should not fail. Rock bolt, you can think something like a reinforcement within the concrete. Then that means bond strength kind of thing. So when you put a reinforcement within the concrete, there should not be any slippage. Bond slippage should not be there. A similar kind of another thing. And it is like this. If LRB is the length of the rock bolt you are providing, and L is the anchorage length, and RP minus RT. What is RT? RT is the radius of the triangle, and RP is the radius of the plastic. So you have to put the rock bolt beyond the plastic zone. If you put the rock bolt in the plastic zone, then what will happen? There will be no shearing resistance. Then it will not work. The purpose of rock bolt will not be fulfilled. So what you have to do? You have to put the rock bolt beyond the plastic zone. How much distance? Up to a length of L anchorage. L anchorage is the anchorage length required for proper bond between rock mass and the rock bolt. Right. So these are the typical cases we use. Limit state equation. Now we have taken a example problem. Same circular tunnel. These are the properties. I think there is no use of. So I have performed the reliability analysis for these two equations. Epsilon is taken as 1% and lambda is taken as 2.4. These are the allowable limit state function value, and we perform the reliability analysis. Now you can see as your support pressure is increasing, then your reliability is better. That means probability of failure is decreasing. What is the meaning of support pressure is increasing? Means you are giving a better quality of support, or you are increasing the thickness of the concrete lining. Obviously, your reliability will be better. And this is the probability of failure with respect to the second performance function. Yeah, this is, as I told you, my PhD student is working. So he has done by different method of reliability analysis. Actually, he will do the work by active increasing approach. That's what I have noticed. This is another case when we have considered the pressure also random. Not that much. Now, just I will take another last example. So this is I have taken another tunnel. You see, here you have a concrete lining, and these are the rock. Right? These are the rock. And again, we have performed the finite element analysis. These are the property of the rock mass, concrete lining, and these are the property of the rock bolt property, etc. These are the property. These are the property of the rock bolt. Then we have performed the finite element analysis. So 4-noded bilinear plane strain element, then rock bolt 2-noded linear 2D truss element. That's truss element, axial force transferring mechanism. And this is the finite element model, and this is the rock bolt are not shown here, but these are model like each one member as a truss, 2-noded truss member. Then this is again the stress distribution, similar kind of stress distribution. Sorry, this is the displacement profile, and this is the von Mises stress profile. You see some of the you see in some rock bolt there are huge stress here and here. Others are not much, but this 1, 2, 3 I can see 4 there are huge stress in the rock bolt. Maybe rock bolt may fail at that cases. Now we have again considered the reliability analysis. We have taken two limit state equation, and we have done some statistical analysis to understand the allowable value. So this is the allowable value for maximum displacement 0.027 meter, and the maximum stress allowable stress is 4.5 into 10 to the power 4 km. Based on these two allowable value and based on these two failure criteria, we have evaluated the reliability. This is the reliability for first failure criteria when you are giving a 200 millimeter linear concrete liner, and when you are giving a 250 millimeter concrete liner, the probability of failure is decreasing little bit, not much, from 543 to 513, hardly 6-7% decrease in probability of failure. But here there is a drastic improvement. Okay, so this I will conclude. So observation, I do not want to make very big things. So CCM is the most common method. Till today we are used CCM, and there are two approach: Hoek-Brown failure criteria and Moore-Coulomb criteria. As I already told that we will prefer HB criteria if it is a medium is predominantly rock, and we will prefer MC failure criteria if the medium is predominantly soil. Right. Finite element method is still most popular in Abacus or ANSYS, though some people still use finite difference software flat for analysis, but I will say that finite element is better choice. And this method DEM, the discrete element method is coming very fast. That synthetic rock mass modeling, which may be the future of stress analysis of tunnel. But till we use continuum model by finite element model. And I have, so reliability part I have not discussed, so I don't want to mention. So there are a lot of methods available actually. Because you cannot apply direct Monte Carlo simulating. This is a big problem. Finite element analysis itself is a big area, so you have to take help of meta modeling approaches. And failure criteria is important. So ultimate limit set criteria and surface limit set criteria. Apart from that, there is another limit set criteria called extreme event criteria. That means if there is earthquake, flood, or fire, then what will be the safety assessment criteria? That is performance-based design criteria we use in earthquake analysis of building structure. Similar kind of criteria we should take care, but those things are not well explored. And in fact, we are doing some research on that field. So with this, I thank you all. So you see, this is a natural cave, tunnel in the old days, and this is our recent tunnel. It is a state-of-the-art highway tunnel with ventilation properties, facility, etc. Right? Okay, thank you with this, and this is the link where you can see the actual tunneling operation. If you want to see, you can see this is a 30-minute video. I don't want to show those now, but if you want, you can show those things.
Okay.
Okay.
Just,
Then, yes, sir.
close your screen, sir.
I have to close my screen. How to close my screen?
Sir, just go to that share, in that share, stop sharing.
Stop
sharing.
sharing.
Share. How to go there? I am not getting it. This one, not this one. This one is my, I think this or this screen. Oh, stop sharing. Yeah.
Stop sharing. Okay.
Yeah. Okay.
Okay, sir. Thank you, sir.
I am accustomed with Google Meet and Microsoft Team. I have not used this Cisco. I have used this WebEx for attending many meetings, but I have not presented in WebEx.
Right, WebEx is better, sir, but
Better, it can take a lot of people also.
Actually, Google is user friendly, and now Google has that was earlier that was free. Now it is paid version. That's why when it
Now we have a paid version, of course. Our student purchase the Google Meet and Microsoft Team. We are taking class, exam, everything on those platforms.
Okay.
Okay.
Sir, thank you, sir, for giving a nice lecture. Actually, participant has asked some
Question, okay.
some
Questions
general
are
questions.
available anywhere in the chat, or they will ask me?
No. I am conveying. I am conveying the question to you, sir.
Okay.
I will interpret.
Okay.
Actually, they have asked, sir, in case of pipe jacking method, when you are constructing the tunnel, pipe jacking method, sir, when hydraulic jack system is pushed into the ground, okay, if there will be any structure, means pavement structure, particularly pavement structure, and pavement structure having the width is 500 mm or anything centimeter or anything half meter, so it will completely damage that structure, sir.
No, actually, you push the pipe below that, below the existing structure, below the existing your pavement structure. What is the total depth of pavement structure? So 1.3 meter.
1.3 meter, exactly, sir.
Below that, you push your pipe. That is recommended. Otherwise, it will disturb your structure.
Yes, sir. Actually, sir, in case of
I have seen here they are doing it now. At present, they are doing every day. I have seen they are making a hole in one place, maybe 2 meter depth. Then they are pushing the pipe, and they are pushing the pipe, and there is a car there. I think they are not using the hydraulic, but they are using some motor is running, and at the same time pipe and water jet pipe both are running together for opening, and material is coming out. I've seen. I was looking to that procedure.
Okay, that is okay, sir. If you see in Park Street area in Kolkata, sir, in Kolkata, in Park Street area, if you will construct a tunnel, there are heavy structures are there, existing structures are there. If you are telling that the tunnel should be go below the foundation or below the base level, if there will be multi-story building, at least the foundation depth is more. So we have to damage that structure, then we will construct.
No, you cannot construct any tunnel just below the foundation. There is a safe distance. Foundation after that, say now tunnel work is going on now.
Okay.
This metro tunnel.
Yeah.
You see, there are calculations. That means volume loss and convergence. So based on that calculation, you have to see at what depth your tunnel should be. And if this depth, if I pass my tunnel, then what will be the stress and displacement along the depth of the tunnel up to the surface? Then what will be the surface settlement? You can calculate all those quantity at the base of the foundation, and now you have to check whether that much deformation structure is safe or not. That analysis is done for each and every building, and actually we have people have done in Calcutta. From Ganges it goes to Esplanade, from Esplanade to it goes to Sialda. Now it is going towards the our airport. No, so all buildings in and around they have calculation. Still there are some fault in the calculation. That's why that mishap happens. No, some people died, some building collapses, and we need to evacuate those buildings. And all those people they put in a hotel for 1 month. A lot of things for 5-6 months. Their work was totally halt. So you have to do the calculations.
Okay. Sir, another.
But the bottom line is that you cannot make a tunnel just below the foundation. No.
Okay.
It is not possible.
Sir, another serious issue is that if you construct tunnel through the rock area, then it's okay. It is understandable. But if there will be groundwater, where groundwater is high, so how to tackle that situation actually?
No, because you remove the groundwater. Remove the groundwater. In Calcutta, it happens. When that was in cut and cover method. No, when you are cutting, water is coming continuously. Motor is running. I can remember my student life days. I used to go for training in organization by bus that time, and I see lot of water and mud is coming out of the tunnel. So you have to do this. But when nowadays people are doing with the tunnel boring machine, na, I was below the Ganges. I told you I visited that places. In the inside, it is like your office, home. Nothing is there. I can share those. I have some videos. Inside, you cannot feel that you are below the river. You cannot feel. Everything is dry. We are taking tea there, some snacks there, because my students are working there. They make some arrangement for tea, snacks. We took it there. Everything is perfect. Because of this tunnel boring is automated operation, na, it say cut for 250 millimeter or 500 millimeter, then it put another support. So it goes cutting at the same time it makes the support. In one day, if it goes for say 100 meter or 50 meter, if it goes in the back side, 25 meter it will cover with the support.
Okay.
That and remaining 50 meter, it has a support within the machine itself. So always you will see the support. That's the beauty of this automated operation. You can check with that video in YouTube video. Fantastic.
Okay, sir.
That's the animated video. Fantastic one.
Okay, sir. So thank you, sir, for giving a nice answer to all the questions. Also, I thankful you accept our invitation. As now offline mode is going, will be from April or March last. So we expect, or I welcome you to visit IGIT Sarang.
I also expect to visit your. I wish to visit your place. I have heard about it a number of times.
Okay, sir.
So whenever things will be normal, you please give me a call. I will visit your places. I will give the same lecture or some other lecture on reliability analysis, whatever you want. No problem.
Yeah,
Even I can teach in the class for 2-3 hours. No problem.
Okay, sir. Definitely, I will call you.
Only thing, how to visit your place? There are direct train from here?
No, sir. Direct train from Kolkata to Bhubaneswar and Bhubaneswar to train is there actually. Bhubaneswar
Bhubaneswar
train
train
and
is,
bus is
okay,
there.
Calcutta to Bhubaneswar, I can go by flight. No problem. From
And
Bhubaneswar, you have to take a train. How much time? How much time?
This will take 3 hours, sir. 3 hours.
Bhubaneswar to your place, 3 hours.
Yes, sir. Yes, sir. Yes, sir.
There are trains are available, day train, night
Trains
train.
are available. We are actually for resource person. We are hiring taxi. So by taxi they are coming actually, and it will take 3 hour or 2 hour 30 minutes. It will take.
Okay, then I will visit one day. So you
Okay,
just make an invitation to me, I will go there.
okay, sir. Thank you, sir.
Okay, thank you.
Okay, thank you, sir.
So I am leaving now.
Yes, sir. Yes, sir. Yes,
Okay,
sir.
I have another meeting. Actually, IOCL is coming in our place for one webinar.
Okay, sir. Actually, professor from IIT Bhubaneswar, he is waiting. Dr. Hanumanta Rao, sir.
Okay, sir.
He is waiting actually.
Thank you.
Now next lecture is there. Okay, sir. Okay, sir. Just on your video, sir.
Hello, Sujit.
Sir, on your video, sir.
No, I don't have any video. Actually, I'm using my desktop computer, so it doesn't have
Oh,
any
okay.
video facility. Anyhow, I will share the slides now, so there is no problem.
Okay, 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 sir, no problem. So, good afternoon, Hanumanta Rao, sir. And he is working as the uh, professor in School of Infrastructure, IIT Bhubaneswar. And his research area includes ground improvement, expansion, soil stabilization, structure measurement, geoenvironmental engineering, and sensors techniques. He has also published many national and international journals. Also, he has acted as a reviewers of many journals. Uh, so thank you, Hanumanto Rao sir, for joining us. And you may proceed. Before that, I also welcome, I think, Gangadhar Reddy and Peri Reddy, Sikant Reddy, Rudra Pratap Singh, and Tanmay Deshpande to our workshop COCEI 2021. And welcome, sir. Now I would like to request Hanumanto Rao sir to share your screen and give presentation. Thank you, sir.
Okay.
Okay, sir.
Yeah, is it visible now? My screen?
No, no, sir. It is okay, 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 sir. Yes, okay.
Now
Just,
it's okay.
just, sir, full screen mode. Keep it full screen mode.
Okay now.
Yes, 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 sir.
Yes, sir. Continue.
It is okay.
Okay.
Continue, sir.
Okay. So thank you, Pradhanji. First of
Thank
all,
you, sir.
very good afternoon to everyone, all the participants, all the faculty members, and I wholeheartedly congratulate Sujit Pradhan and his colleagues for conducting this TechCube 3 short-term course and giving an opportunity to share some of our valuable work which was done by my PhD students and master students for the last couple of years. So this is a small work being done by one of my PhD student, Mr. P. Srikant Reddy. So he is on the verge of completion. So he is extensively working on the expansive soils, and these soils also preferably of soils which were collected from different regions across India. So I also congratulate Sujit for successfully conducting this short-term course on challenges and opportunities in civil engineering infrastructure. In fact, it could be a beautiful platform to share some knowledge which was developed over the period of time by various students to different students. I hope the information will be shared by this presentation is useful to many students for taking up their BTPs or MTPs or even research projects. So all my details are available in this slide. So my phone number and my email, everything is available. So those who are watching this video, you are most welcome to approach me at any point of time. So in fact, you can come for some kind of internships or co-sharing the MTech thesis, or if you want any kind of help for conducting your MTP or BTP, you are most welcome. So let me share. So today I'm going to present the talk on expansive soils characterization for chemical elements and their influence on swelling properties. So this topic is in particular on a specific thing, that is the chemical elements related with the expansive soils. So this is very something new. So before that, I don't need to give any kind of an introduction about expansive soils. So I think this is one of the topics which was probed by a lot of people over several decades. So if you talk about expansive soils, so we always hear about only the negative aspect of these expansive soils, but there is the tremendous positive aspect also, especially if you look at the utilization of the bentonite soil. So bentonite is categorized as extremely swelling soil, but this is the soil which is used as one of the successful barrier material. So that is on the positive side. But majorly, we see expansive soil as a negative aspect, because when you construct or when you try to use the soil as a geomaterial, or when you try to construct structures on or in the expansive soil in some or other way, so you might be encountering some kind of the problem. So that normally we term it as the volume change. So there are two aspects. When there is a change in the volume, we term it as a swelling potential. While when that particular volume change is happening, if there is some kind of overburden exists on that particular soil, so the amount of the pressure that exerted is called as a swelling pressure. So this is external meaning, but internally, I will talk about how the swelling potential and swelling pressure is exerted by each and every particle, especially at the particle level, in the subsequent slides. Since the expansive soils are spread over almost several states in India, so almost 20% of India is covered with these expansive soils. And you go to any country, in most of the countries, you can find expansive soils. So they are basically present in arid and semi-arid regions. Uh, so in India, if you come to India, 20% of the land mass, or approximately 3 lakh square kilometers, so is covered with the black cotton soils. In India, so the expansive soils are typically represented with the black cotton soils because of their color. But I also should mention here that it is not only the black cotton soils that exhibit the swelling behavior. There are other kinds of the soils also that exhibit. As we know, when you talk about expansive soils, we always talk about a specific mineral, that is montmorillonite. So these are some information reported by the different people in different countries. The revenue loss or loss damage to the structures in terms of the monetary. So across different countries, as you can see, there's a almost there's a huge loss. Huge loss means they basically cause some kind of the damage to the structure. So when the damage means in terms of cracks, especially when there is a crack and the building loses its aesthetics, and thereby you need to go for some kind of a repairing. So those are called as a structural damages. So these are the few examples, the damage to the structure. So here you can see there is a shrinkage. If the structure is built on the expansive soil sample and damage to the road, or whenever you deal with any kind of an expansive soil, cracking is the common phenomenon. So this cracking is literally attributed to the shrinkage phenomenon. So and this is also related to or interlinked with the tensile strength capacity. So if you look at carefully, everything is interlinked. Swelling, shrinkage, tensile capacity, cracking, all are interlinked. So one is the manifestation of the another. But everything starts with the soil particle. So that is the clay particle. When you talk about expansive soils, we basically talk about 3 or 4 fundamental clay minerals. So those are One of the thing is kyanite. Everybody knows about it. Next is smectite. Next is illite. So other clay minerals are there apart from these three, like a chlorite or several other clay minerals are there. So I'm not going to talk about those things. But if you look at these four minerals, among these four minerals, smectite is categorized as the swelling soil. Now also try to understand the difference between the soil and the mineral. So every soil is a composition of some amount of minerals, and each mineral is again a combination of a particular chemicals. Now the same thing can be understood from this slide. So here I have categorically shown the group name. This for example, if you take the kyanite, or it is otherwise called as a kaolin soil. So kaolin, then in kaolin, the kyanite mineral is dominant. But it is not only the kyanite mineral, there is also quartz mineral present in almost every clay soil. However, if somebody is asking how much is the proportion or content of this one, then that particular mineral is predominant. In case of the kaolin soil, so kyanite mineral content is exceeds in fact 80 or 90, and the remaining is the quartz or other minerals. Similarly, in case of the illite, it is illite mineral. So in case of the smectite, it is the montmorillonite mineral. Now we should particularly discuss about the mineral montmorillonite. So again, I hope by now you understood. Smectite is a soil. In fact, sometimes you also see smectite designated as a mineral. Then in that case, they say it is a bentonite soil. So in bentonite soil or in smectite, montmorillonite mineral is predominant. Okay. Now, the other things also you have to understand. We are talking about the soil, and there is something called as a clay particle, and there is something called as a mineral. So I will try to distinguish about all these things in the subsequent slides. Now, when we talk about the mineral montmorillonite, you also might have heard of. A montmorillonite may be predominant with the calcium content or the sodium content. These are the two varieties which have been majorly used for air as a barrier material. So this is the chemical formula, or these are the chemical formulas of various minerals. So the second column talks about the soil type, and the third column talks about the mineral name, and the fourth column talks about the chemical formula. Suppose if you take the combination of Al2 Si2O5 into so OH4, this combination of chemical formula designates the mineral called as a kyanite. Okay, but if you look at the kyanite, it contains the chemical elements of aluminium, silica, oxygen, as well as the hydroxyls. Similarly, if you look at the mineral montmorillonite, its chemical formula also differs. So if sodium is dominant, then that is called as a sodium montmorillonite. If the calcium is dominant, then that is called as a calcium montmorillonite. Which otherwise, so apart from the sodium and calcium, the other rest of the chemical formula is remains same. Again, if you look at carefully, if you look at the montmorillonite mineral, so the chemical elements are sodium, aluminium, magnesium, silica, oxygen, then hydroxyls. Okay. Now, which component of this chemical formula dominates? That predominantly governs the behavior of the entire soil. Okay, as I told you. So if you look at any soil, and if you try to quantify the mineral content in that particular soil based on this chemical formula, so based on this chemical formula, so I can say that there is also presence of the quartz, which is a simple silica, but so and compared with the whole montmorillonite, the content of the quartz or the silica is quite less, maybe around 10% or 15%, or even lesser than that. While more than 80 to 90% is only the montmorillonite. So these are the pictures of different minerals. If anybody has not seen, so these images were captured with the help of scanning electron microscope. So these are called as a stacks of clay particles, stacks of clay particles. So if you have undergone your soil mechanics course, you might have understood, especially in the clay mineralogy, the stacking or layers of the clay minerals. So those stacking can be evidenced from these SEM images. So this is a stack of clay particles in case of kyanite mineral, and in case of the illite mineral, and in case of the montmorillonite mineral. As you can evidently see, so all three varieties are different. So thereby the behavior of the kyanite should be different than the illite, which again should be different than the montmorillonite. So this is morphological these are called as a morphological characteristics. Based on the morphology, we can say that the minerals are also different. Now among the chemical compositions, so those are also different. So this is how the soil behaves or governed by the mineral component, and depending upon the content of the mineral, their external behavior changes. Now for those who doesn't have any kind of an idea how the 2:1 or 1:1 structure of clay mineral is represented, so this slide gives a vivid understanding. So first you start from the single oxygen or hydroxyl element, so then other cations like calcium, sodium, magnesium, potassium, and so on and so forth. So when they're packed in a particular arrangement, depending upon their charge or the geometry, so they form either tetrahedral structure. Best example is silica, or octahedral structure. Best example is sodium or aluminium. Now, if you keep this silica one adjacent to the another in a series way, or so this aluminium or sodium one right adjacent to the another in particular series, then they form a seat. So that's it. So this is represented in the form of either tetrahedral or octahedral. Okay, so this is how the tetrahedral and octahedral name has been evolved. So the tetrahedral or octahedral represents the arrangement of the silica or the aluminum atoms, so kept one adjacent to the another. However, when they are adjacent, that means there is a mutual common sharing ions between each adjacent atoms or the chemical elements. So then when you talk about the 1:1 semi-basic unit, so as we have seen, so this tetrahedral and octahedral, when they are stacked, so again depending upon their bonding, so for example the prevalence of ionic bonding or the prevalence of the covalent bonding, and they may form 1:1 semi-basic unit or 2:1 semi-basic unit. So 1:1 means one tetrahedral over the octahedral. 2:1 means octahedral is sandwiched between the tetrahedral. So these are basic units. And when these basic units are again formed, those are called as a layers. So these are called as a layers of mineral. So as you can see here, suppose if you look at the kyanite, so this is the combination of two layers. Similarly, halloysite, combination of the two. So 1:1 semi-basic unit leads to the formation of two variety of minerals. Those are kyanite and halloysite, and the remaining all clay minerals are basically forming from the 2:1 semi-basic unit. But one particular interesting thing is that there are two things: one stack and another stack, or once two seats, above two seats and below two seats are interconnected with some kind of the bonding. So this bonding has a very important role in the overall behavior of that particular clay mineral. So all these minerals, all these names are belongs to the clay minerals. So kyanite, halloysite, pyropylite, smectite, vermiculite, illite, chlorite, mixed layer. All these are clay minerals only. But how to distinguish them? That depends upon their bonding. Now let us try to understand little intricately. Now the bonding between these layers.
Okay.
Okay. Yeah, can somebody switch up the mic? Can somebody mute the mic?
Pedireddy Sikant actually. He has
Acha.
yeah.
Srikant, can you put the mic? Okay.
Okay.
Yeah. So just let us try to understand how these layers are interconnected. So there are variety of bondings which interconnect these layers. So as shown in this. So that include, for example, if you look at mica or illite, so it is bonded with the metal cations. While if you look at the chlorite, it is with the hydroxide seat, octahedral seat. And if you look at the montmorillonite, it is with the combination of water molecules as well as the exchangeable cations. While if you look at halloysite, it is only with the water molecules. And similarly, layer double hydroxide, it is with the exchangeable ions. So depending upon the presence of the bonding between the layers, so the behavior of the entire clay differs. Now let us also try to understand another important aspect, that is the thickness of each layer. So if you closely examine, and several people has reported the thickness of each layers. So in case of the kaolinite, the thickness of the two sheets, so one tetrahedral and one octahedral, is around 0.7 nanometers. While in case of the mica, so it is 1 nanometer. So in case of the chloride, it is 1.4 nanometer, and vermiculite 1.5 nanometer, and smectite it is 1 to 2 nanometer. And here it is clearly shown which mineral is expanding type and which mineral is non-expanding type, and what could be the possible reason. Now for this you need to understand the bonding between the layers very importantly. Suppose if the bonding is the hydrogen bonding, so the hydrogen bonding is very strong, so therefore you can't expect any kind of swelling in those clayey soils. Similarly, some clay minerals are attached with the potassium bonding. Even potassium bonding also strong. So therefore, you can't exhibit or you can't anticipate any kind of swelling in these kind of clay minerals. On the other hand, it is in particular noticed in montmorillonite mineral. So that is the bonding is predominantly with the oxygen bonding. So which is also called as a Van der Waals bond. However, this bond is very weak. So because of this weak bonding, so the montmorillonite mineral particularly expands. So the expansion takes place between two sheets. So this is one sheet and this is another sheet. So here the expansion takes place. So I will also demonstrate further. But an important thing that you should understand from this presentation is, suppose if the layers are interconnected with the hydrogen bonding, so you can't expect any kind of the swelling because it is very strong. It doesn't allow the separation of the layers. Now, other clay minerals where the potassium bonding prevails, since it is also very strong, so you can't expect any kind of the expansion. While on the other hand, so montmorillonite mineral, the bonding oxygen, so one can expect some kind of the swelling. Now, as I highlighted one in one of the previous slide, so there are two important things that you need to understand when you try to deal with any expansion soil. So the chemical composition, that is in the form of elemental or oxides. So in this table, which has been shown here, is called as a oxides composition, like SiO2. Oxides means if I take oxide, the O component out, then that becomes element, like a silica. So if it is combines with oxygen, so then that becomes silicon oxide. So SiO2 are Al2O3, are Fe2O3, TiO2, K2O potassium, sodium, magnesium, calcium, so on and so forth. So the chemicals also present in the expansive soil or in any general soil, as well as at the same time the minerals also present in the expansive soil. Now between these mineral and chemical contents, which one controls the behavior of the expansive soil? Because this is the part, although it is addressed, but not to that extent. Because if you look at expansive soil, everybody understood about something like, because of the presence of the montmorillonite, so the soil exhibits the swelling behavior. Okay, but it is not only that. Suppose if you look at the waste material, so there also minerals present, and particular minerals are dominant, but their behavior is governed by not mineral, rather it is governed by the chemical compositions. So therefore, it is equally important to understand both perspectives, the chemical contents perspective as well as the mineral content perspective. And moreover, up to certain period, there was no advancement in the instrumentation, where at that time they used to simply understand, okay, because of this mineral, so there was behavior of this one. But now there was enough sophistication in the instrumentation. Today we are in a position to even quantify the content of the montmorillonite, the content of the kyanite, or content of the illite, alongside the contents of the chemical parameters. So therefore, depending upon which component is higher, we can able to understand whether that particular soil is governed with the chemical parameters or the mineral parameters. Now, why this is important? Because in expansive soil, as we see, it is the problem with the swelling or the shrinkage. So unless you understand intricately these chemical compositions and the mineral compositions and their quantification, you are not in a position to provide a reliable solution for the remediation, say in case of expansive, say for example expansive soil, to mitigate the swelling behavior. Now in my presentation, I'm going to talk about what would be the influence of these chemical parameters on the swelling soil. Now, when I talk about the chemical parameters, they are basically available in three forms. The first one is called as a total form. That means, as I showed in the previous slide, like oxide composition, that comes under the total form. Okay, so from the total, suppose if you try to treat these total form of chemical elements, some amount of the total form gets leached out. For example, uh, if you do acid digestion of some soils, then there is a possibility of the leaching of like a sodium, calcium, magnesium, so on and so forth. Those are called as a leachable form of chemical elements. On the other side, on the other side, so there is a possibility of the exchange of ions, cations or anions, only on the surface. These are not inbuilt chemicals available in the soil. Like a total form, it is like image of that particular soil. That means this soil is made up of that particular chemical composition. But when you talk about the exchangeable form, some chemicals which are externally adhere to the clay particle, as is shown here. Suppose say this is the clay particle. So like here potassium, calcium or sodium, they are coming from the external. Here coming from the external means, for example, from the pore solution. Suppose if this clay particle is attached with or immersed in pore solution, if calcium or potassium ions are available in that pore solution, they will try to adhere to the clay particle. Now, why this adherence happens? So that's because, as you know, so each clay particle is characterized for having a negative charge. So this negative charge is because of the isomorphic substitution, but that happens at the crystalline layers at crystal level. Okay, so that's during the formation of the mineral itself. Now, in order to neutralize the existing negative charge on the surface of this clay particle, it tries to attract the cations which is having a positive charge. So it tries to attract the cations until the entire charge gets neutralized. So it is immaterial whether it is a sodium or calcium or potassium, so on and so forth. So it keeps on attracts all kinds of the cations. Now, when it is attracting or adhering these cations, they will form something called as a diffused or double layer. That is also called as a diffused double layer. So, this diffused double layer and this cation exchange capacity is said to be causing the swelling in the expansive soils. Okay, so again, try to understand. So what we are talking is the totally different. So we are talking about total form of chemical parameters which are with which the soil is made. Okay, the another thing is when the chemical elements are supplied externally and which were adhered to the clay particle, those are called as a exchangeable cations. But when there is an exchange, so that exchange happens in place of something else. For example, the lower valency can be exchanged with the higher valency, but the exchange happens only at the surface. Now, as I told, so this slide explains the surface of the clay particle is characterized for negative charge. So in order to neutralize that negative charge, it attracts all positive cations. All positive cations. Now, this attraction or adherence, will it strictly confine to only the surface of the clay particles, or can they enter into the seeds? So in case of the expansive soils, as can be seen from this here, so these each seed represents the clay particle. So they are attached on the surface of the clay particle. Now, so when there is an attachment, or when these cations try to ingress between the clay particles, so there is another kind of a pressure that acts, so which is typically called as osmotic pressure. So that's a different. But when they try to ingress between the clay particles, because of their electrostatic forces, they will try to separate the particles, or they will try to push the particles, clay particles, little bit apart. So that is called as a swelling. So this moving apart is called as a swelling. So these moving apart is purely this electrochemical phenomenon, as you can understand from this slide. So there are no other external forces. Now here all these cations, they are coming from the external source. And you can see a variety of cations. Now one particular important thing is that, so as I was discussing about the exchange of cations. Now, can every soil has equal exchange capacity? So no, the answer is no. So it depends upon, few soils can exhibit low cation exchange capacity, while the other soils can exhibit higher cation exchange capacity. So most of the natural soils, they will exhibit very low cation exchange capacity. But if you look at the bentonite soils, they exhibit very significantly high cation exchange capacity. So that's why, so the swelling in bentonite soils is very high. So more cation exchange means more separation between the clay particles. More separation means more swelling. Now, where these cations or exchangeable cations adhere? So there are different places. So at the surface, at the edges, then interlamellar spaces, that is between the seeds. So then that interparticle spaces. So all are responsible for cation exchange capacity or adherence of the cations. Then as a result, we can see the volume change as a total phenomenon. So although the separation is happening at the particles level, at clay platelets level, but when volume change is happening, that is the manifestation or the reflection of the contribution by the whole of the soil mass, not because of only individual particle. Okay, so that's why the volume change is so huge. So, and as you know, each clay particle is nano size, 1 micron, 1 nanometer, so on and so forth. And if you take 1 gram of bentonite, the specific surface area of this 1 gram of bentonite is almost equal to 700 square meters. We can imagine how many lakhs or millions of the clay particles they are there, and how much amount of water that they can able to absorb onto the surfaces, on the surface or on the edge or on the interlamellar spaces, and that every that absorption, how much it can cause the volume change. So this is the swelling mechanism. So the exact mechanism I explained in the previous slide. The external manifestation is like this. So when you add water to the clay particles, so all these H plus ions and OH minus ions, they try to adhere to the clay particle. So as a result, they will try to move the clay particles apart. So that is called as a separation. So this happens only when you feed the water. And since the clay particle has a negative charge, they will try to attract the positive ions, that is H plus. And so this is how we can able to understand. So when the clay particle is in dry state or when the clay particle is in expansion state. So when they imbibe the water or when the clay particle absorb the water, so a whole the water layer forms all surrounding the clay particle because the charge exists all surrounding. So on the surfaces there is a negative charge, on the edge there is a positive charge. So therefore all whole surface attracts the water, and when it is absorbing the water, it forms some kind of the water layer, as you can see. As you can see. So even this picture also shows so how the expansion happens in case of a non-expansive mineral, that is kyanite. So it doesn't allow the separation of seeds because it is a strong hydrogen bonding. While in case of the smectite, so there is a huge expansion. So this separates the seeds, top seed and bottom seed. So in between, there is an ingress of all exchangeable cations. As can be seen here, it could be water molecules or some other cations. So this is one seed, while this is another seed. These two seeds are separated by ingress or exchange of cations. Water, it could be water or any other cation. Now here, suppose if you add only water, there is a possibility of only the H2O molecules. But what if that particular clay got contaminated with some pollutants? So, and that pollutant may contain the sodium or potassium or magnesium or any other chemical. So that's how. So the other cations comes into the picture. And so this is the same images of the fully expanded montmorillonite. These are called as a clay flakes or clay seeds. And this is all. This is picture which shows clearly. There is one of the fundamental question that comes to everybody's mind is. So we said the swelling is because of the absorption of the water, and even if you take the kyanite or the montmorillonite, so there is a possibility of negative charge on the surface. But why only the montmorillonite exhibits the swelling? Why not the kyanite? So the basic reason we can understand from this one. If you look at the absorption of the cations or the water molecules in case of the kyanite, they are predominantly confined to only the surfaces. But in case of the montmorillonite, so these cations or the exchange will happen between the seeds. So when they try to ingress between these layers, as can be seen in this picture, so they will try to push apart these seeds, so which is manifested as the swelling. So more is the ingress of cations, more is the swelling or volume change. Okay, I hope now it is clear to everyone. So though we talk about or we designate kyanite is a clay mineral, montmorillonite is also a clay mineral, but only montmorillonite exhibits swelling, but not the kyanite. So this is how we can also understand from micro phenomenon to the macro phenomenon. Now, on the other side, so as I highlighted about the swelling soils, so nowadays one of the buzzword is how to utilize the waste materials. So we are, if you look at the literature, people are using a variety of waste materials for mitigating the swelling behavior of expansive soils. We can use, as long as it doesn't have any kind of external harm to the soil or the human beings, we can use any kind of the waste material so that could able to chemically react with expansive soil and thereby mitigate its volume change behavior. But one important point that I highlighted in the previous slide is the chemical compositions. Now, in this slide, we can clearly understand how the chemical compositions differ from waste to waste. So, for example, if you look at the fly ash, so silicates and aluminates are dominant. But suppose if you look at the steel slag, so here calcium is dominant. And if you look at the red mud, the iron content is dominant. Okay, now when these particular chemicals are dominant in that particular waste material, is it good to expect the similar behavior among these waste materials? So it is not. That's why every waste exhibits its unique behavior. That the fundamental reason is the differences in their oxides composition. Okay, but it could also be because of the difference in the mineral composition. So I'm not talking about that component, because since I want to concentrate or I want to highlight only the oxides composition influence or the chemical parameters influence. So I'm just putting forth in front of you how these chemical compositions differ from waste to waste material, and how or why these waste materials will exhibit uh, the different behavior. Now, it is also important in another aspect. So, for example, you want to say neutralize, sorry, if you want to mitigate the expansive soil. Now, how do you understand their compatibility? That compatibility can be understood only when you understood the chemical compositions of the waste material along with the chemical composition of the material with which you are dealing with. Unless there is a compatibility between these two, then it may be reversal effect. For example, a lot of studies we have seen that if expansive soil is treated with the lime, the swelling reduces. But if the same expansive soil is treated with the copper, the swelling increases. Okay, so this is purely because of the incompatibility in the chemical compositions. So this is one of the important point that everybody aware, so that when you take a decision, so it effectively works. So this is suppose again how the same element can differ from waste to waste material. So this is difference in SiO2 in different waste material, and difference in aluminum content in different waste material, difference in iron content in different waste material, and difference in calcium content in different waste materials. So now this slide explains so how those, because we use normally all cementitious additives or the chemical additives for mitigating the swelling behavior. So how can they influence? This is one of the paper or one of the small study we have done it, and we try to understand how the conventional additives, that is non-cementitious additives, perform when you compare with the chemical additives. Mostly when you use non-cementitious additives, their uh, means influence is the physical. For example, they can act as only filler material, so they can remove the white space. It cannot remove, they occupy the white space in fact, and thereby they may not be allowing the clay particles to expand. On the other hand, suppose if you try to deal with the chemical additive, as is seen from this slide, the performance of the chemical additive is bit superior to the non-cementitious additive. While cementitious additive like a lime, so it falls between the chemical additive and the non-cementitious additive. That means if you use non-cementitious additive, we can expect the least result. While if you want highest performance, then you must select the chemical additive. So this was the small study done by one of my PhD student. Now here, now you can able to correlate. So the whatever the discussion I made in the previous slide. So how the chemical composition of the waste material is equally important when you want to treat the natural expansive soil. Suppose if you select the active chemical waste materials which can able to react with the expansive soils and thereby reduce both S and Sp, which otherwise you will get the least performance. Similarly, here this slide shows the effect of the valency. Valency means suppose if you take the potassium, sodium, calcium, magnesium, lithium. So every chemical parameter has a different valency. So even that valency has also some influence. So here suppose if you take lower valency as the least influence, higher valency as the highest influence. So both are swell potential and swell. In fact, it is a reverse. So they show a reversal effect on swell potential and swell pressure. So let me present some results of my PhD student work. So we have collected a lot of samples of expansive soils from different states across India. So we almost collected 40 to 45 soil samples. So these are the gradational characteristics, particle size distribution. You can see there is a huge difference in particle size distribution of these soil samples. But anyway, that is immaterial. Now this is the plasticity chart, which is showing so almost most of the soils exhibiting the liquid limit of greater than 50%. Now, so if you have understood the geotechnical engineering or if you have undergone any expansive soil characterization, you must have seen one of the fundamental thing is that if a given soil is exhibiting liquid limit greater than 50, then we can categorize that particular soil as an expansive soil. Okay, so the same thing can be seen from this slide. So almost majority of the soils are exhibiting the liquid limit greater than 50. So therefore we can say most of the collected soil samples are expansive in nature, maybe expansive in nature. So not yet confirmed. And all the soils are falling under the category of CH, high compressibility, because all of them are above the A line. Now, since I was talking about the soil, the clay particle as well as the montmorillonite. So let us try to distinguish let us try to understand intricately again. So there is a natural soil. So this natural soil we have collected some sample, we brought it to the laboratory. There we have done the gradational characteristics. From that we found that say, yes, this fraction of the soil is clay. For example, 50% is the clay, remaining 50% is silt or sand. But it is not only the clay we are dealing with. Okay, and it is the mineral that we are dealing with. So this is the SEM image of the clay particle. Now how to understand about the mineral? So these are the SEM images of the minerals. So this is the SEM image of the montmorillonite. Now this montmorillonite can present only in the clay particle. So try to understand. First of all, the clay fraction in your soil is the 50%. Now within this 50%, how much would be the montmorillonite content? So that means there are two parameters that can control the expansive soil behavior. The first is what would be the clay content within that expansive soil, and within that clay content, how much would be the percentage of the montmorillonite content? Is it 0 or 5 or 90 or so on and so forth? Okay, so these are the two important things you should deal with or you should understand. Now, since when we have done the literature survey, we couldn't able to find the relationship between this clay content and the montmorillonite content, because this is one of the essential parameters we need to understand. So these are some relationship that we have developed. So we have done a lot of free swell index test on almost all the soils that we have collected, and we also try to validate our results with some literature. So here we can see the relationship between free swell index versus the clay content and the free swell index versus the montmorillonite content. So again, this montmorillonite content is part and parcel of the clay content only. So nothing to do with the external soil. However, you can take the montmorillonite content directly as a fraction of the clay content, or we can manifest this to the overall soil behavior. So this is up to you. Okay, usually, so the montmorillonite content will be taken as a whole soil phenomenon, not as a part of the clay content. But so here it clearly shows. So free swell index increases with increase in clay content. So increase in clay content as well as the free swell index increases with increase in the montmorillonite content. So here, but if you draw the FSI with the clay content, so you can see a lot of variance in the results. But the same thing if you draw with the montmorillonite content, so it shows a clear cut trend. So this is because when you talk about the clay content, So in the clay, so again, the montmorillonite may be 100% or maybe other minerals also can exist. For example, when I talk about the clay, so this can comprise of the kyelinite mineral or illite mineral as well as the montmorillonite mineral. So I do not know how much is the relative proportion. And again, so all the three variety of clay minerals able to absorb the water because they form the diffuser double layer. But when they are forming the diffuser double layer, there is a kind of an interference among these things. So that also need to be taken into account. So for estimating the free swell index, this is one of the fundamental reason. It is well said in the literature that although you take two soils exhibiting the same liquid limit or the same clay content, but they still exhibit different the swelling behavior. The reason is attributed to the difference in their the montmorillonite content, not in the clay content. Okay. So then since we are talking about the clay content and we are also talking about the montmorillonite content. So again, so let us see how these two are related. Sorry. So this is the relationship between montmorillonite content versus clay content. So when we try to draw the relationship, we found that up to about 40% of montmorillonite, so there is a increase in montmorillonite content with increase in clay content, but thereafter it's almost some kind of a scatter. So you can see between, but it started from I think about 10% or in fact about 15%. So then it ended up to 70% because 70% is clay. But if you, these are only the natural expansion soils. So these doesn't include the minerals like bentonite soil because in those soils the montmorillonite content can be as high as up to more than 90%. So these are all natural expansive soils. You can see huge scatter in the results. Well, this scatter could be of several reasons because when you talk about the montmorillonite content, we need to use a specific technique called as a XRD, X-ray diffraction mission. So to initially to establish the X-ray diffractograms, and from there we need to determine the montmorillonite content. But in the process, there are a lot of parameters that can impact the montmorillonite content determination. In fact, that is a very tedious task. So the scatter could be related to the process involved in determination of the montmorillonite content. And moreover, so though we determine the clay content by the hydrometer, so since we deal with the nanoparticle size, so the possibility of committing the error in clay content determination is quite low, but still there is a possibility. But this is the relationship between montmorillonite content versus clay content. Okay, so from macro to micro, from macro to micro. Now, additionally, so the two things that was discussing is in two forms the chemical parameters are there. One is the total form and leachable form, or total form and exchangeable form. So in case of the expansive soil, there is a presence of the sodium content and the calcium content. And if you review any literature, they say that the entire swelling is only because of the presence of either sodium or the calcium. So therefore, what we have done is we try to see the correlation between the swelling parameters versus the content of sodium or the calcium. So here T designates the total calcium present in that soil. Okay, and L designates leaching of this calcium from the total calcium. So that's why the Ca total is expressed in the form of a percentage, while leaching is expressed in the form of a milligram per kg. And this leaching may be 100% or maybe 10% or in between any range. Okay, so we do not know, and as such, I also do not have any idea how to confirm how much percentage of this leaching from the total. I don't have any idea, but I know. So there is a total amount of calcium exists in that soil, and from that soil, certain amount of calcium can leach out. So, and we do not know whether this is the realistic parameter or the leachability is the realistic parameter. So therefore, we try to correlate both total form of the chemical parameter calcium and leachable form of the chemical parameter calcium related with the free swell index, and we have seen a beautiful relationship. So this is, you can see in almost all the things. So with calcium or with sodium, in both cases there is an increase of free swell index with increase in the calcium or the sodium content. Now, one question that everybody should ask is, why should I relate with the calcium CAT or NAD, and what will happen to the exchangeable form? As I told, the exchangeable form is although responsible for the swelling potential of the expansive phase. Here we want to understand, suppose if the, because determination of the exchangeable potential every time is a difficult task. While suppose if you have a facility of XRF, it is easy to determine the total form of calcium or sodium. And if I know the relationship between the swelling versus the presence of this calcium or the sodium, I can easily envisage what could be the possible swelling potential. So this is the primary intention of drawing the relationship between swelling property versus total calcium or total sodium exist in that soil. These two parameters are nothing to do with the exchangeable form. Okay, so these calcium and sodium are the images of that particular expansive soil. So as I told, the main intention is to understand for how much percentage of the calcium the soil can exhibit maximum swelling. Here you can see if the soil contains approximately between 4 to 6% of the calcium, or between 0.3 to 0.5% of the sodium, so then that particular soil can exhibit maximum free swell index. Or alternatively, in their leachable forms, so we can understand between 50 to 70 for in case of the sodium, in case of the calcium, or between around 120 or 130 in case of the sodium. Okay, so in your, suppose if you take any expansive soil, if you do the XRF analysis for determining the calcium content and the sodium content, and if you try to correlate, if you try to determine the free swell index, then if you try to relate, this is the relationship you will get it. Or alternatively, so if you are unable to conduct the free swell index test, or you want to know based on only the chemical parameters, so then this kind of relationships are very handy. Now there is another advantage also. We already know that, so these soils are expansive in nature. Okay, and if I want to treat this expansive soil, I have to use some kind of the chemical, as I shown in the previous slide. Either I can use the chemical additive or cementitious additive or non-cementitious additive. So forget about the non-cementitious because there is no chemical reaction involved in it. Especially when you are selecting the chemical additive, it is very important to understand how much would be the presence of this calcium total, this sodium total, because these are the chemicals which are ultimately going to react with the externally added chemical additive and thereby mitigate the overall swelling behavior. So without understanding this one, then we always end up saying that, so any two given expansive soils, although they have a similar clay content, they still exhibit the difference in the swelling potential. But that gap can be overcome when you try to make this kind of the relationship. So these are the relationships for the Atterberg limits. So that is a liquid limit with sodium content and calcium content in total form and leachable form. Because when you talk about the expansive soil, so initially we use Atterberg limits as one of the preliminary parameters for scrutinizing whether the soil is expansive or no. So that is the reason we try to correlate this liquid limit and the plasticity limit, the plasticity index with the sodium or calcium content. In fact, so when we try to relate, everything has shown a beautiful correlation. So there is a increment in the plasticity index. You can see there is a perfect increase in free swell index, increase in liquid limit, then increase in plasticity index. They increased, reached a peak, and then decreased, and then decreased. So there is a beautiful trend. So then, so these are the relationship we got it with the exchangeable form. Now again, so when I talk about NaCEC or CECEC, when I say these two terms, so this is not internal component of that particular soil. This sodium is externally induced in the pore solution, which is adhered to the clay particle. So which is adhered to the clay particle. Now, so they, suppose if you introduce the sodium alone into the expansive soil, then we can see one kind of the swelling behavior. Or if you try to introduce calcium as a pore solution, then we can see another variety of the swelling. So here it is related with the liquid limit. So you can see in all previous correlations, so there was a increment reaching a peak and then decrement. But when we try to correlate liquid limit with NaCEC, there is a continuous increment of the liquid limit, then thereafter it became saturated, but there was no decrease in that. So similarly, even plasticity index also. So there was a continuous increment of the liquid limit or plasticity index. So then it reached a peak value. So similarly, we also try to draw the relationship for swelling potential as a function of the total sodium or the total calcium or the leachable sodium and the leachable calcium. So again, so they have a tremendous implication, especially so to identify the potential chemical additive so that so your swelling potential is minimum when you try to treat that particular expansive soil with the chemical additive. So these are the relationship with the swelling potential versus sodium and calcium chemical elements. So these are the swelling pressure correlations with the total sodium or total calcium. So one particular thing that we observed is in case of the SA, so there is a well-defined correlation between swelling potential versus the sodium chemical parameter everywhere. But we did not find such correlation when we try to correlate with swelling pressure with the total chemical parameter. As you can see in the bottom slides, there is a lot of scatter or there is a definite trend. Suppose if you look at here, uh, the left side, the figure number A. So only in this case, there is increase in SP, it reached a peak and then decreased. But suppose if you look at the graph C and D, we cannot say there is a perfect increment reaching a peak or decrement. So there is some kind of an so undefined trend. So that trend is not well defined. Yeah. So that's what is all my presentation. So if you would like to ask any, this is a small presentation, but I thought it's very informative. So if you would like to ask any question, you are most welcome to do so.
Okay, sir.
Yeah, Suchi.
Yes, sir. So this is a very good presentation, and you know, you actually we gain knowledge about different characterization of expansive soils that
Yeah.
earlier we have no idea about that that much properties and that much
Please
characteristics
stop
are
the
there.
sharing slide.
Sir, stop the sharing, sir. Sharing of your slides.
Just a minute.
Okay.
Maybe it's next application. Let me show you how to do this one. I'm also little bit confused.
Pratik?
Sir, in that one share, you go to the share, in the bottom there will be share icon will be there. There will be, you can stop sharing.
Here, nothing is showing here.
Pratik,
That bottom,
Okay, got it.
Just
Stop share. Yeah.
yes,
Stop
fine,
share.
fine.
it's okay. It's okay, sir. It's okay.
Yeah, now I got it.
Sir, one question is that actually,
Yeah, what?
in case of pavement construction, actually,
Yeah.
so there are different layers actually. So if in subgrade level, if there is a content, let a black cotton soil, but expensive soil, any type of soil is there, means
Yes.
we have to stabilize that expensive soil, or we have to increase the thickness. Means how to design actually that pavement structure, any type of structure, not only pavement actually.
Yeah. So I understand. So actually, my one of the primary purpose of giving this presentation also for the same thing. There are two school of thoughts here. Either you can go for stabilization of that expansive soil, but when you stabilize it, again the problem is, so many people reported lime stabilization, cement stabilization, or when you use any other chemical, it is highly effective. But the effective became a qualitative term. Okay, so sometimes in few of the expensive soils, when they are adding the like 2 to 4% of the lime content, it could able to mitigate the expansive nature. But in some cases, it was not working. Okay, there was no universal solution for that. Now, in order to arrive at that universal solution, so it is necessary to quantify the how much is the montimole net content, or to quantify these chemical parameters. Because understanding that chemical reaction is the most important. Once you are understanding that crux, so then you lose the stabilization with anything, it works.
Actually, sir, we have seen in village expressway or NH, this type of things are they are doing actually.
Yeah.
In case of sir, village roads, actually in black cotton soil or any type of soil they are present there. Sir, engineers are not doing actually.
They are
Just
not doing.
they removed some portion, means some centimeter depth, then
Yeah.
adding any good type of soil or good type of like that. Actually that is feasible because in village road that is low volume roads, sir. That is low
Correct.
volume roads. Is it feasible some or more or less?
It is feasible, but only to some extent. It is not a permanent remedy.
Sir, another thing, when actually we are designing the road, or people, even if government of India or NRDA, they are asking for they are concentrated only on the severe value, sir.
Correct.
Severe of the subject soil or anything else.
Yes.
But in case of, sir, you have told about different characterization, different types of parameters that the soil deal with. But
Yes.
but they are asking about the severe test only. Means what is the need of, actually that is a practically problem that we are facing. Engineers are asking about that. Means in soils, sir, there are a lot of, you have source different chemicals are there, different
Definitely.
variety limitations are there, but
Yeah.
they are only asking the severe value, and liquid limit is less than 6%. Means how they are doing actually, sir, please. So advice actually means.
See, now you can do one thing. Suppose say, now based on this one,
Okay.
now I have shown the relationship between this liquid limit versus calcium or sodium content.
Exactly, sir.
Okay. Now, suppose say your liquid limit is 70.
Exactly, sir.
How much should be my calcium or sodium content so that the liquid limit comes below 50, and thereby that soil is acceptable for the construction.
Exactly.
So that's what is main idea of developing all these correlations.
Yeah.
Okay. Thereby you can avoid the problem of that liquid limit. Now another the major problem that you are saying is that CBR. So that is
only they are saying about the severe value.
yeah.
Nothing. We are talking about the different shear test, usage test, or any type of test. But
Yes.
no, government India has given guidelines that severe test is enough. All are not required actually. Once you written severe.
Yeah, let's see. Somebody has to scratch the point.
Yeah. Sir, you have one thing, one red mode, then waste material actually red mode. Red mode is there.
Yes, yes.
Actually, how effective this was as compared to that let fly ash, pond ash? It is better or what is the effectiveness by compared to other waste material like fly ash or GGBS, the GGFS and pond ash? Is it
Uh,
effective? Red mode, sir.
Effective means, see, definitely there will be some reduction of the swelling potential,
Exactly.
but more than effective, we have to see the compatibility and their consequences. Because
Exactly.
the third point we are missing. See, everybody simply adds lay fly ash or bottom ash or slag or red mud with the expansive soil.
Sir.
But what happens in the due course of the time, if there is some kind of an adverse chemical reaction by adding that, this nobody is understanding this one. How to understand that effectiveness?
Exactly.
See, that is the core now. See, for
Yes,
example,
sir.
if you look at red mud, it
Yes, sir.
comprises of the iron oxide. So it is said that the iron oxide also forms some kind of the monolayer of water film on the particle surfaces. Okay, and how much it will be, how long it will be retained, I do not know. But when
Okay,
this
sir.
water layer is available to the expansive soil, it is bound that in the due course of time, if water is not available within the soil, but if it is available on this iron particle, it try to attract. So it try to adsorb that water layer because of this electrochemical forces, and
Okay.
thereby, so sometimes like initially you may see the reduction,
Exactly.
but in the long run, the phenomenon may get reversed.
Okay.
Okay, because of this chemical things.
Okay. Means any type of waste material we are using in the stabilization for any type of purpose. Means we can't tell this material is better than that material. Means each and every material have their own properties and
Oh,
accordingly we have to analyze,
yeah,
then use it in the field.
yeah. But see, suppose say it is very difficult to convince the others.
Exactly, sir. Exactly.
Okay, now there then we can show these results. Yes, we have done this one. So suppose
Exactly.
if this chemical composition is confined to this percentage, then the
Exactly, sir.
liquid limit is below 50 or the swelling potential is below 10%, something like that we can show, then we can
Okay.
convince and then go ahead for the construction.
Okay, okay. Actually, sir, what are doing in our college, in the front side of our college, actually there is 100-kilometer road are constructing NHI actually, and
Okay.
they have done MOU with Nalco, and
Okay.
their supplies are fly ash.
Okay.
Freely.
Okay.
When they are depositing fly ash in the over the road and by adding water they are compacting, people are complaining. Why you are using this one? This is ash type. The strength will be less. Means that is up to their limit.
Yeah.
So to educate people is necessary, sir, actually. Uh,
Yes, 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 yes.
yes, that is, sir. I think that is the most important. We,
Correct, correct. That is most
we know that is good, okay, but to understand people, it is very difficult, sir. Actually.
Yes, yes, that is true.
uh, okay, sir. Thank you, sir.
Yeah, thank you.
Pratik, is
Sir.
conclude.
So thank you, Dr. Hanumantarao sir, for accepting our
Yeah,
invitation. And
thank you, Pratik.
definitely participants are appreciating your presentation today. And they
Thank you.
definitely capture some key points from your presentation. Thank you, sir, for this.
Yeah, thank you, thank you.
Thank you,
Okay,
sir.
thank you, sir. Okay,
Okay.
okay, thank you, sir.
Well, tomorrow you will announce something. So dear participant, tomorrow the same time will be live on YouTube. So the time will be 4 p.m. Thank you.